Hello, hello.
Hey,
Nice to find you again, Thomas.
hey, Luca, how are you?
I'm good,
Friday
I'm good.
again.
It's Friday and I got a haircut in the meantime. So for those of you who consume binge watch the Thunder sessions, you will find some modifications. I can say the same for you, Thomas.
Well, I didn't get a haircut, unfortunately. Uh, it's not that easy to, like, at the moment. But I'll be next.
No, no, I like the style. I like the style. Awesome. So last week, what we did was we created a small MLP with a linear, a ReLU, and then another linear, and we wrote a Triton kernel from scratch from it, and then we went in, acquired that model, and then went in the trace and wrote a transform that allowed us to replace the linear or op with the custom kernel that we had. And of course, this is interesting because you can write your own linear. It's great for learning how to do that, and it's great for understanding all the details of that process. And I think we learned a lot last week. Uh, but where these things become actually interesting is that by knowing how to write a Triton kernel, you can now merge operations together. So we talked often about the fact that fusing operation together saves you a lot of time shuffling bits back and forth on your GPU. And so ultimately your outcome will be a faster model because you save time and you don't wait on transfers. So this week I would like to go from the linear ReLU linear, where the two linears are replaced with a Triton kernel, to a linear ReLU together, fused together into one kernel. And then if we have that kernel, the Triton kernel, then we can write a transform to say, okay, pick the linear, pick the ReLU, and replace those two entries in the trace with just one entry, which is my handwritten kernel. And we'll see where that leads to. So that is good. But before doing that, we got a question on Twitter, which is great. Um,
Yeah,
so
tell me.
Bibraj, who is also a great contributor to Litzer, which is something we as Lightning launched in the last couple of weeks. It's a great serving inference library. It's super powerful, but at the end, it's also simple, and we like simple and powerful, and we try to embody it throughout the stack. So check it out, Litzer. But he asked a very interesting question, which is, the ones of you who have been following the latest trends have seen that a team at LinkedIn released Liger, which is a set of optimized kernels, particularly for training, so pre-training, fine-tuning LLMs. And there are a set of Triton kernels, and he asked, how does this compare with Thunder? So, Thomas.
Yeah, so it's not really. So the kernels themselves are really, really great and huge, huge, huge achievement by Byron and the entire team. And this part is like outside the scope of Thunder. But then what they are doing currently is they monkey patch models in order to use these kernels, which is, of course, a nifty way, but in a way it's also not that principled. And so this is where Thunder comes in, and maybe we can show this next week or so.
Yeah, that
Um,
would be great.
that Thunder can now hook into these kernels and take a vanilla libGPT model and fine tuning, and then run this fine tuning on using the Liger kernels automatically without having to modify the code. And so these optimizations can really like ship with the integration layer that's not specific to one model, but that's generic and can apply to any model where the kernels like apply where the functions they need are from the kernels. And in fact, many of the kernels map one-to-one to PyTorch operations or functions that you would typically see in an LLM. But so, for example, at the very end, they have a nifty trick where they fuse the final linear layer, which outputs the logits for the whole vocabulary, and they fuse it with a cross entropy in order to not materialize this giant logits tensor. And for example, there you need to like fuse two operations, and we'll see an example of fusing things today, right? And so
yeah, exactly. So
if you wanted to, you could submit a patch using Thunder with Liger, like right after viewing this episode, hopefully, if we can.
yeah, that would be great. Yeah, and in fact, this episode is kind of the preparation for us, and we wanted to do this independently, for us to showing how you can integrate something like Liger kernels. And so we built it up, like we wrote one kernel, replaced it in the last episode. Today is two kernels, fuse it together, and there will be a simple fusion, and we'll also compare the performance a little bit and see that it's interesting. And then next week we're gonna do the same operation but on a real model and with real optimized kernel by the Liger team. All right, I think without further ado, I would just go into it. We maybe draw something, we maybe not. We'll see, but let's get into the code. We're gonna get the code from last week, so it's very easy to follow, and then we'll tweak that. But we'll make sure we go through all the details, even though we touched upon them last week.
Yeah, let me share my screen here. Can you see it?
Yeah, I see the awesome Lightning Studios interface. Oh, by the way, but before we start, we're hiring for compiler position and research engineers to help us out with Thunder. So please, if you're liking this, if you have some experience, if you know kind of the internals for PyTorch or JAX or whatever framework, please reach out, send your CV. Thanks.
Yeah. So here we are. I'll pull up the notebook from last week. And so we started out with the little MLP that Luca already mentioned. So we have this sequential model with a linear, a relu, and a linear. And so we added the bias here. I will remove this now to make my life a bit simpler. And then we looked at what Thunder makes of this. And we see that, well, in the basic case, the relu will be taken by NVFuser. Oh, now it's taking a few seconds to start up currently.
Yeah.
That's the live demo. And so what did I do? So let me. Okay, now here we are.
Yep.
And so
great.
What we have here is like the linear, and then you have the relu, which got morphed into an NVFusion, and then you have the second linear. And what we did is we used Triton and wrote a kernel. And yeah, that's elaborate enough. And if you want to know more about it, I would recommend watching the last episode. And so there's a driver function, if you want, that calls this matmul kernel. And that just is the matmul. And I'll show you an awesome trick here. So we had this before. We had like this. If I like increase the size of the matrices a bit, then we can see that it still works. And well, obviously with larger matrices, it gets a bit slower. But it's still relatively fast. It's just taking it's taking 1,000 loops. Um, and 7 runs, so it takes a few seconds to do the measurement. And we see our round kernel takes about 125 milliseconds, and using Torch Matmul with the same is a bit slower. So in this case, and we've hard-coded the optimization parameters for simplicity. Triton can also like automatically try different configurations and pick the fastest. But so here we're actually a bit faster with the Triton kernel than with the stock PyTorch Matmul, which is not an easy feat, but that is, of course, Triton doing all the magic. Okay, and then we had our Matmul executor. And so what we did is we defined a meta function, which is a function that explains or that tells Thunder, if you pass in tensors of this shape, then a tensor of that shape will be returned. Like you have the first dimension will be the first dimension of the first input, and the second will be the one of the second input. And then, of course, we need also to tell Thunder what to call, and this will be just the matmul function itself. And we registered this as an operator with our executor here. So
yeah, it's interesting. Like I was thinking, no, it's okay. Yeah, I was thinking that, if we match something on the trace, this is live brainstorming, to make this even more seamless, maybe in the future we could say, have this that is a replacement for this other thing, and it's behaving the same way from a meta perspective, right? And we already could do that, but we could do that in a way that it's even more streamlined.
yeah,
We're brainstorming about ways to onboard to make using Thunder as cognitively simple as possible. So that's why we're talking about that all the time. Okay, great.
yeah. So and then we used like this to register an implementation for the torch NN functional linear, which was taken from this trace here, right? We saw that this is recorded as a torch NN functional linear, and so this is what we took here as what we implement, and we had this checker function that allowed us to decide like whether we want to take this, and we only use like plain matrices with 2 dimensions, and we wanted no bias in the linear. And the transform just expresses like what linear does in terms of our new symbol. And we had this, and with that we could see that, well, yeah, one thing is it works, and the other thing is we now see that we have the mymatmul here and here, because we inserted also the transpose. There's the transposition here that is usually absorbed into the linear. But so this is where we were last time, and now we already discussed that we wanted to fuse like these 2 bits, the rel and the linear, right? And so
yeah, one thing that we may mention is like the permute. Does it take time to do the permute? What is the implication? Because before I didn't have those ops, now I have those ops. Like what performance wise does it have any impact?
The permute is a pure metadata operation. So with each tensor will be a blob of memory on the GPU, but it will also have on the CPU certain information like how large each dimension is, what is the pointer to the GPU memory block, but also the strides, which kind of say how much you need to go in which direction. And so this permute is just changing this metadata, and that is generally very fast.
And I have one other question then. Since in our Triton kernel, like one could write a kernel with assumption that the tensors coming in are contiguous in the sense that they go from slowest moving index to fastest moving index. And so the strides are essentially monotonically decreasing, going right. But Triton gives us the ability to deal with strides directly, right? So
Right.
it doesn't really matter. So we shouldn't need to see a contiguous there because Triton lets us operate with non-contiguous tensors in that matmul that we wrote.
Yeah, so obviously there is a caveat to this that, of
Yep,
course, the memory layout of the tensor will have an impact on performance
exactly.
because of how memory accesses work. But of course, we could like optimize it. And so one reason why we have this transposition here is exactly because it has been considered more efficient to have the contraction dimension as the fastest moving dimension, if you want to, for both the inputs.
Nice.
Okay, so what I wanted to show you here is to go back to the initial trace we had. And here we have, this is L-torch relu, and this will be Thunder torch relu.
This is before Thunder did this thing, right? So you went back
Right.
into the last traces because we have all the steps available to us. So one of the great things you can do is say, okay, let me see the trace at the beginning, the trace afterwards, after the passes, and so on. So now we got to the first one. So we see what was acquired unmodified.
Right. And you can even see like the lines here that caused Thunder to record this. Unfortunately, here it's just a line inside PyTorch. Maybe we should like put the user code there and skip the PyTorch line.
Yeah.
But yeah, okay. So should we start looking at getting the fusion going?
Yeah, for sure. Would you start with the Triton kernel at the ReLU or
Yeah,
works the other way?
let's do the Triton kernel first. So
Nice.
we saw that in the Triton kernel there's these const expression parameters that are well, they're magic, but they are also things that Triton will compile separate kernels if they change. So I will add one of these, and let's just call it do relu. Of course, you could also take a string. I think they do in the example that is basically here. This is the Triton matmul example, right? And so we default this to false because it will be a Boolean in the end. And so if there is a do relu, then we need to maximize the result with 0, right? And so we just write it here as if it was normal Python. And so here this would be result equals tl.maximum. And the trick is here to know that maximum takes the maximum of two things, whereas max is special as a reduction. So tl.maximum of result and 0, which is what relu does, right? And so we can do this.
Wait,
And then
that's it?
that's it. It's that easy. And so if we do relu equals true here, equals false here too, and just pass, and maybe we put that before the internal parameters, do relu equals do relu, and so that's it here. And now if we do the same trick here with let's take this line here, we can take this test whether we compute the right thing, and now we do relu true, and here we need to do torch relu torch matmul, And voila, there it is.
That's
So we
pretty
have a
impressive.
fused kernel here, and yeah, no, yeah. And what's also neat is that if we look here, like what does it mean in terms of performance? And we have Torch Relu, Torch Matmul. And of course, this is kind of unfair because, well, so the matmul here, the torch matmul, will have to materialize the tensor, and then it needs to read the tensor again for the relu and write the result, and it creates two tensors here. But so we see that our implementation is virtually of the same performance as without the relu, and we have like 200 microseconds more for the relu operation here. So this is like a 10% performance penalty for adding the relu manually, and here we get it virtually for free for 1 or 2%.
Yeah, it's kind of like you, and we're not advocating for Triton versus CUDA. There's a place for everything, but the power of being able to control the low level this way, it's hard to beat. Like if you have to go through like 10 layers of abstraction to do something like this, that's tricky. If you can use your thin framework approach to pull this off, then from a learning perspective, it's there to see. It's immediate. We talked in the abstract about fusions, and of course, coming up with an engine that fuses things is very hard. It's not easy at all. But having a model in front of you and trying fusions out for the specific case you have in front of you, so it's about the scope you want to tackle, right? It's really empowering. I find it extremely powerful. So now we'll also do the thing where you control where exactly in the computation trace you want to place your things, and you have full control of that. And there's nothing in between you and being able to express exactly what your question is. Oh, what if I do that? And with Thunder now, you can do that exactly. So let's do that.
Right. And so we will do like the easy way, and we could do the linear here immediately, and maybe we do this. My linear meta, and this will be input, weight, and bias, and I need to assert that bias is none, and then I can just call return matmul int weight transposed, and I want mat linear relu, right? I don't want linear. And so I will do relu equals true. So I implement this, and of course I need the meta function too. This was supposed to. I wrote the impl, so let's do it this way.
Yeah.
Meta, sorry about this. And imp weight bias, and here we return a tensor proxy again, but this time, because we have the transpose, we have that the shape is a dot shape 0 and then b dot shape 0, because this time we implement a linear which has the transpose built into the implementation here.
Yep.
And now we register the executor again, so my matmul, my linear relu is, and we just do it to the matmul executor, and we register the operator my
linear relu,
linear relu, and the meta is my linear relu meta, and the implementation is my linear relu implementation. And so would be awesome if that worked, but of course
extra pair brackets.
Yeah. No, what did I shape? Oh, I forgot here the equals. Okay.
Oh yeah.
So now it worked.
So now basically our Thunder now understands the symbol. There's a new symbol in Thunder, the new operation that expresses linear relu together. That wasn't there before because Torch doesn't have it. And we just added it to, registered it, means added it to what Thunder can reason about.
Right. But so now Thunder doesn't know yet, and we did this register implementation last time, but this only works if I have a single thing to replace here. And so now we need to actually find the things to fuse and fuse them. And in Thunder, we have what we call transforms that will transform the execution traces. So we will look for linears where the output is consumed by a relu, right? And so let's jump right into it. And so now this is a bit like elaborate. So we need from Thunder core transform.
Yeah, and maybe this is an area where we will make things a bit more ergonomic in the future. But following this exactly will give you the unfiltered view of what needs to be done in this case, like with no sugar on top of it, which will be like a bit elaborate, as Thomas has said, but at the same time not too complex. So,
right,
let's get into it.
If I have this transform, I can have various parts where I can hook into. So transform module would transform the module. We don't need that. This is for loading state dicts. We don't need that either. But here we have transform traces pre-prolog, which runs right after getting the program. And so this is where we will hook into. And so this takes 3 positional parameters, the 3 traces, so the prolog trace, the computation trace, and the epilogue trace. And we will focus, and it takes some keyword args. We will focus on the computation trace here because that's the only thing we need to modify for the fusion.
Yeah, just to mention, go back a few episodes. Prolog is what takes your module and transforms it into a functional representation of your computation, which is the computation trace. And then epilogue goes from functional back to module object-oriented world. That's roughly the thing.
Right. And so I mentioned that we need to check whether we find it linear and then it is consumed by relu. And so for this we need to know like which functions take which arguments, and there's a function what you need to find in Thunder again. There's a function producers and consumers, and you pass in the computation trace, and this will automatically tell you for any proxy variable that's in the trace where it is consumed, which is like very handy. And because we want to modify the computation trace, we will create a new one. So new computation trace is Thunder core trace from trace, and we will build one based on the computation trace. And now this will copy all sorts of administrative properties. What it will not copy is the actual instructions. And so we need to now go over the instructions and add them to the new trace. So for bsum in computation trace bounds symbols, and now the easiest would be like new computation trace dot bound symbols.
Just to remember, bound symbols are whatever the computation trace is made of, which are function calls. And the bound symbol is the symbol, which is the function, let's say, and the arguments, which are together, they make up the bound symbols in a nutshell.
Right.
So we're iterating over all the steps in the trace that we see, and here we're basically copying every symbol, bound symbol on the other side. And so the new computation trace is the same as the old one, essentially.
Right. And then it's a good habit to tell the user like where the trace came from. So this is constructed by fused linear relu.
Yeah, because then when you go back and say last trace is 1, 0, 1, 2, 3, 4, it will actually show, oh, this is constructed by blah, blah.
Right.
And so you can recognize it.
And so we need to return the 3 traces, even the ones that we didn't modify. And so
it's a new computation trace.
The new computation. You want the new one? Okay, I'll take the new one.
Yep.
And the epilogue trace. And so this is the most basic transform, but of course it doesn't transform anything yet. Right? But I already prepared this consumers. And so what we want to do is if the the symbol, and now it gets like really funny, the sum of the bound symbol is the actual...
Which is the function name, the instruction name, without the arguments.
The function itself, the bound symbol...
Yeah, the function itself, not the name.
And the symbol is the function itself, so it will be torch, not torch, thunder, torch linear. And so the first thing we do is we get the consumers of b.output. And now we need 2 things to happen. One thing is, of course, it needs to be consumed by the relu, but the other thing is it can't be used anywhere else, right? So our condition would be if the length of the consumers is equal to 1.
Sorry, it was bsim.output, right?
Sorry? Oh, yeah.
Yeah.
And the symbol of the only consumer is thunder torch relu. Then we know we have a winner here. And so we can assign this to relu. And then we need to actually make a new bound symbol. And that is slightly different. So we can just override the bsum with bsum from bsum. And now we need to say what we want to have different. And so what we want to have different is sum is my matmul. No, sum is my linear relu.
Yep.
And we want a different output because now we just want to return the relu output, right?
Yep.
And now there's one of these weird things you have to do, unfortunately. So you need...
we'll remove this part. Close your eyes, go for a drink, get some water, and until we write this. But
Right.
if you don't add this right now, you'll get in trouble. So please pay attention.
Yeah. So we really need to get
Yeah, kill it in a fire.
this.
Yeah.
And so no, not new visum like this. It looks really funny too, right? You see that shouldn't be necessary.
Yeah, it shouldn't be there. Anyway, it's all
Okay,
good.
so actually I lied, and we have a third condition that we want to have, and this is like visum dot args, and the second arg should be none, right? The bias.
Yeah, the bias. Yeah.
And so just to be safe. And so now we have we have consumed the relu here, and the new bound symbol will be added to the computation trace. But we need one thing: we need to skip the relu now. We don't want the relu in the new trace, so we say we start a set like vsums to skip, and this is a set, and what we'll do is we have vsums to skip, and we add relu to this, and if we have here if vsum and vsums to skip, then we want to not process this, right?
Yep.
And so that's it. That should be, unless I've forgotten something, that should be like our thing. And now all we need to do is we add here transforms and add, I'm never consistent whether to take tuples or both would work. Okay, so let's do this. We have the matmul executor and see if it works. And it works. But what it do now...
It's funny that you find it funny, but I also find it funny. Like, this is the real... When we mean this is how the sausage is made in the subtitle for the session, like, this is how the closest to how the sausage is made we've ever been.
Right. And Luca has me live coding all these things. But on our 100th episode, Luca will do all the coding.
Absolutely, yeah.
Okay.
But we have like 94 to go, so I'm good. I'm safe for now.
But what did I do now? No, it didn't. Nothing happened here.
Did it print? Did it?
Something went wrong.
This is the -1.
Oh no, it did my linear relu.
Yeah, exactly. It looks so
all went
clean
well.
that yeah.
I was confused because this should probably not be there, so let's clean that.
Yeah, exactly. Yeah.
Okay, take everything
because
from the old symbol is a bit dangerous, because this decomposition that would have been registered, that wasn't valid anymore, and now it's gone, so we're safe here.
We need to make it a bit more ergonomic here too.
But
see, like what we did is we took the thing, we pattern match it by hand, but it's fine because you see exactly everything that needs to be done. So if you want to write a transfer that does matching a bit more in a more generic way, a sophisticated way, you can do it. We'll also add something in there to do that without doing it fully manually, but that was great. So now we have a computation trace that fuses with our fusion thing. And so if you had a large model with a lot of matmul relus, it would fuse all of them, right? Not just the first.
We can do that. I mean, we can...
It's kind of like 40 minutes in, so I'm not sure. Oh yeah, you can do it. Like, it's fine. Exactly.
Yeah, Luca thought that I was going to recode everything for 40 minutes, but
nope.
But the beauty is that, of course, I can just rerun the jitting on my new model, and now I have tons of fuse relus here, right?
Oh, nice. Look at those.
Awesome. So that's what I wanted to show.
Yep. This is
Anything-
what a fusion transform is, right? So this is how you connect a fuse kernel to a computation. So it's awesome. Now we have all the ingredients to kind of understand what's happening next week when we take the Liger kernel, one of the Liger kernels, or more than one, we'll see, probably more than one at this point, and apply it to a model without messing around with monkey patching and stuff, but transforming the computation. One more advantage of that is that you can then compose transforms, and then we get into compositions maybe in the future. Well, maybe certainly in the future.
Yeah.
But for now, we'll not care about that. But that's a very important thing, because it's not that we don't want to change or monkey patch is bad. Like everything works. Like, if you want to monkey patch, monkey patch. The thing that if you do that, then you lose the ability to compose with other things that monkey patch themselves, because you either monkey patch one thing or the other. And here we are kind of reasoning through a computation and transforming it and evolving it with one or more transforms that behave well, if you make them behave well with one another.
Right.
All right. That was awesome. I like this episode a ton. So thanks a lot, Thomas. I didn't draw anything. I actually had to ride home because I forgot my iPad in my studio here, but that wasn't useful for anything. But that's great. So I think everything checks out. Maybe we can also publish this this notebook so that people can replay it, and we link it in a tweet or on LinkedIn right after. So thanks a lot, Thomas. It's been great.
Thanks, Luca. Always awesome
Yeah.
to do this with you.
Yeah, same. Likewise, we couldn't do it without you. So that's, but it's also very, very, very nice. Of course, this moment is very cherished. Next week is preparation week for PyTorch conference. So unfortunately, you won't be able to be there for accidentals that happen.
Yeah.
Unfortunately, but
Going
fortunately,
fast is very good with GPUs, not so safe with cargo bikes.
yeah, that's the last message. Yes. So unfortunately, you won't be able to be there at PyTorch conference, but a bunch of other people from Lightning will be there, including myself. We have a Thunder talk and we have a keynote slot. So hope to find people there, and otherwise, talk to you next week.
Yeah.